여보세요? 상원이, 도원이 있나? 도원아, 그거 내가 잠깐 늦었는데 링크 좀 업로드해, 다. 그래, 땡큐. Alright. Hello, everybody. It's very nice to meet you. Actually, I expect we can do the offline lecture in this semester, but because the COVID-19 situation is not released, that's why we have to do our lecture in online. I just talked with the department office. If everybody agrees to do an offline lecture, then we can do the offline lecture. As I wonder if you and everybody agrees to open the offline lecture for mechanics and materials. So I'd like to ask your opinion. Actually, I prefer to an offline lecture instead of online lecture because it is very difficult to check the response of students. Now, what I mean, I cannot figure out if students follows well my lecture without having problems because I can see your face. So what do you think? Is it okay to do an offline lecture, or it's better to keep in the current form of online lecture? So what do you think? So let me know your opinion. Alright, so we'll do the YouTube lecture in this semester. So I will post my lecture note before the actual class time, so that you can download my lecture note and then you can participate my lecture in the chatting window provided by this YouTube channel. Alright, so let me start my lecture in this semester. The title of my lecture is Mechanics of Materials. Okay, so Mechanics of Materials. And then here, my name is Ji Kwang-seop. This is my name. And this is my email address. So if you have any questions or comments regarding my class, and also any subject discussed in the classroom, so you may send me an email. Your questions and or your comments and everything is very, very welcome, because it's better than better than no response, isn't it? And this is my office phone number. The last digits of my office phone number is 3324, and then my office is on the third floor of engineering hall, 공학관 3층, the first room. And then my office hour, actually, if you open the portal site, there is an office hour, but I put the office hour because there is space in the portal. Anytime is okay, but I'd like to have an appointment before we take a time for your questions and comments, okay? And this is my homepage, the structure.korea.ac.kr. So if you click this link, then you can reach to my homepage. So if you click here, for example, you can look around my current hot topics of researches. So each buttons on, let me, I need an arrow. Where is an arrow? Okay, I need this. Okay, so then here you can see my current hard research topics, and here I listed some of my papers with a higher number of citations. So for each buttons, each buttons correspond to the subject that our lab is dealing with. And then the second button here, if you click professor, then you can see my information. So this is my contact point, and then also my curriculum vitae, my 이력서, the 공문 이력서, and also the English version of my resume. And this is my research topics, and then my current and activities in Korean. And I'm also a guest professor at China University of Petroleum, so I have to visit Qingdao for a month every year. But because of COVID-19, I couldn't visit there. I didn't visit there the last year and in this year either. Okay, only after the COVID-19 problem is resolved, I can visit this place again. So I'm taking a PhD students from this university. After finishing master's degree from that university, and then the students continues his PhD programs at Korea University, supported by Chinese government. And then here, this is my citation matrix, and if you click this, and then you can find how what kind of research articles are cited by other researchers. And then also, if you click this, and then you can find my current members, and of course these are some old members. And then also this one, if you click the publications, you can find the list of publications that I made during my research activities. Okay. So this is the outline of the class. The subject covered in this class must be the most essential part for civil and mechanical engineers. Okay, and then the reason that we put this class in the second year of undergraduate study is this class provides really the fundamental and the elemental block for further studies. Okay, only after you master the concept discussed in the mechanics of material class, then you can continue your study into higher levels. Then, for example, after taking this mechanics of materials, then you can study structural engineering or the structural design too, and also you can discuss the subject in the geotechnical engineering based on the mechanics of materials. So basically, we discuss all the ingredients for further discussions in the field of civil engineering. Okay, so without having the information in mechanics of materials, we have real big difficulty for further study. You understand? Okay, this is like how do I say? So mathematics, okay, it's like the basic mathematics in high school study. This is so important. So I'm very proud of taking this class for my students. And then here we're gonna discuss the fundamental concepts like, you know, design, what's design, and what's analysis of, especially for the structural systems. Okay, then here as the most important concepts, we want to discuss so-called stress, in 우리말 응력. Okay. So stress means the stress means in 우리말 응력. Okay, and then here the strain means 변형률. So I wonder if we have international students in this classroom, but the majority of students are Korean students. That's why I'd like to introduce, you know, the Korean terminologies to all the definitions. And here the deformation. Deformation means 변형. Okay, deformation is 변형. And then displacement. Displacement means 변위. Okay, 변위. So here, make sure that here the 변위 is defined in the vector space. Like, let's consider the x1, x2, for example, in two-dimensional space, or depending on authors, they use x, and instead of x1 they use y. Okay, but same meaning. But it's better to play with x1 and x2 instead of x and y, because we have a shortage of notations. In the case of 3 dimensions, we use x and y and z, but sometimes we have to deal with multiple dimensions. Okay, more than just 3 dimensions. In that case, we have shortage of the notations. That's why for me, and also for most of advanced researchers, they use, you know, this x1 and x2 initial notation. For example, in the case of 변위, displacement, we check the position of particle P, and if particle P is displaced, okay, displaced to the next position, the P prime, then we can define the position vector here. Say, to represent this position vector, for example, I want to consider vector R of particle P. And then if it is displaced, okay, then we can define new vector. Okay, new vector. Say we're gonna consider new vector for P prime. Okay, so if you subtract the original vector from the displaced the vector for the displaced positions, then we can obtain the displacement u, vector u of particle P. It is defined as rp prime minus rp. Okay, this is the definition of displacement. Make sure that displacement means here that is a vector. Okay, vector. So deformation is we'd like to represent the state of deformation. Okay, state of deformation. Then what would be the prerequisite? 선행 과목. Okay, 선행 과목. What is a prerequisite for this class? And then the prerequisites for this class include vector mechanics. So you need to understand the vector stuffs. Okay, you have to understand what's coordinate and what's projection. Okay, projection and what's unit normals. You have to understand that. And also you need to have information for statics. The static means for you, probably you already took statics, isn't it, right? Statics is probably you discuss statics in 공업역학 class, or if you come from other universities, probably statics in Korean it is called 정역학. Okay, 정역학. And then as the counterpart to statics, we have dynamics. Then this is called 동력학. Okay, 동력학. Do you have any questions? Now, how do you like my iPad? Does it look better? Up to the last year, I used real, paper, real paper, and I used two different cameras. But in this semester, instead of using real paper, I'd like to use my iPad. Okay, so hopefully it's better than the real paper. Actually, for me, it looks okay. Okay, then what is the textbook? The textbook, I want to use Goodno's textbook, so Mechanics of Materials. And then this is the title of this textbook is Mechanics of Materials. Let me tell you a funny story. Actually, the Mechanics of Materials is almost Bible to, I think more than 80% of universities in the world where the civil engineering, the subject of civil engineering is discussed. Okay, it's almost Bible. The original version of the textbook was written by Timoshenko, and Timoshenko is called the father of civil engineering, and he built the foundation of civil engineering education. So he structured, he built the structure of the mechanics of materials and the structural analysis. Okay, and basically this textbook follows Timoshenko's approach to engineering education. Then after that, Timoshenko, the textbook was evolved to Timoshenko and Gier. It is a second generation, kind of. No, like 1.5 generation. And then this textbook, this textbook was evolved to Gier and Timoshenko. And then it becomes Gier's textbook. It becomes Gier's textbook. Sorry about it. Gier's textbook. And then Gier's one becomes Gier and then Goodno. As you see here, Goodno. And then it becomes, now the current version is Goodno and Gier. This is what happened. But basically, the structure of the textbook is exactly same as Timoshenko's original textbook. Honestly speaking, I was taught mechanics of material by this textbook written by Timoshenko. It's almost Bible in the sense of mechanics of materials. And then I'd like to give you a reference, the Paitel's textbook. The same class, in the same class is taught by Professor Kang in the second semester. He used the Paitel's textbook. This is also a good textbook. So I'm using Gier's textbook, the Mechanics of Materials, written by, originally developed by the Timoshenko. So I'm using the 9th edition, but as I told you, the original version of the textbook or the structure of textbook was developed by the Timoshenko. That's why basically almost no difference. Okay, so if you have the older version of the textbook, it's basically no problem. At the end of this lecture notes, I put all the homework problems, and you can just refer to homework problems from my the lecture presentation. Basically, you wouldn't have any problem even if you don't have the correct version of the textbook. You understand? Okay, this is class calendar. We wanna start in the first week, and we wanna discuss the introduction, and then we will talk about the problem of tension. So if you have enough time, and then the second week we'll talk about compression and shear, and then we'll move to the actually loaded members, and then we'll talk about torsion and the shear force and bending moment, and then we wanna discuss how to calculate stress in beams, and then we'll take the midterm examinations. Okay, then after midterm examinations, we'll talk about the advanced topics of the beams. For example, how to calculate stress, bending stress caused by the bending moment, and also the stress by the shear force. And then we'll go into the material point. And here we want to talk about the concept of stress and strain in different directions. And we'll consider a very special case of plane stress. The plane stress problem is commonly used in engineering approach, many engineering approaches. The plane stress is called 평면응력. So we will visit this concept in 12th week. And then I will talk about deflection of beams and the statically indeterminate structures. So if you have time here, probably we'll discuss some part of statically indeterminate structures even before the midterm examinations. And then finally we'll talk about columns, columns to discuss the buckling. So here the subjects of columns is for the buckling. Maybe I need new pages. In the part of columns, we'll talk about 기둥. So column, the reason that we talk about 기둥 is we want to talk about buckling. In 우리말, 좌굴, or instability, 안정성, 안정성. And then here the beams. Beams means girder, bow. Sometimes beams are called girders. Girders. Girders is called in many Korean textbook or design code. Simply they call girder. And then here the terminology of torsion. Torsion means 비틀림. In Korean part is 비틀림. The actually loaded member means 축하중 부재. Actually loaded members 축하중 부재. Any questions? 축하중 부재. And then this is my evaluation policy. So we will assign, we'll have homeworks every week, almost every week. Not almost every week, but at the end of my lecture note in each section. So I put 20% for the homeworks, and then for participation 10%. So including your questions and comments. If the participation means it doesn't mean attendance. Actually, I have to check the attendance of students in this classroom, but in this online lecture system, it is almost impossible to check your attendance. Actually, honestly speaking, I don't care about the attendance. And then for the midterm examinations, we have 30% for the credit. And the final examinations, 40%. By the way, this is my long-term policy. All the homeworks should be submitted in 1 week. Officially 1 week after the homeworks are assigned. So otherwise, my TA is gonna be very busy because of this homework evaluation. So please submit the homeworks in 1 week. And then the minimum credit to pass this class is 30% out of 100%. This is really fun. In almost in every year, so I have some of students who want to negotiate with me for their credit to pass this class. But look at this, the meaning of 30%. The meaning of 30%, for example, so if you submit all the homeworks in the right time, then you can get 20%, okay? 10%. And then even if you don't have any information for the exam problems, so if you take my class with good care, then probably you can get 10%, isn't it right? So this is minimum credit to pass this class. The 30% is not that high. So if you pay attention to my class, then I believe you would get 30% out of 100% without having any problem. That's why I put 30% as the minimum requirement for my classroom. Okay. All right. Here I'd like to introduce a diagram. So here this is my diagram. So I developed this diagram, and then I show this diagram to my students in almost any class. Okay, any class, whether I'm teaching undergraduate students or graduate students. So here, so we have only 3 conditions. Okay, for the structural analysis, we need only 3 conditions. So you have only 3 conditions. So please make sure about it. Okay. So although in your textbook, if you open textbook and also other reference books, and then they provide in different solution techniques depending on problems. But don't be confused by their suggestion or their way of explanation. You have only 3 conditions to deal with your structural systems. Okay. So I guarantee. So if you don't solve your problems with these 3 conditions, please let me know. Okay, so I can explain you how we apply the 3 conditions to solve your problems. Okay. So in structural scale, so we have 2 conditions. The first one is force equilibrium. Okay. So force equilibrium is called 평형 조건. Okay, 평형 조건. Actually, this 평형 조건, this force equilibrium, play between the external force and the internal stress. Actually, I don't explain you the internal stress yet. I will tell you later. Anyway, the force equilibrium is a relation between the forces, the externally applied forces, and there's some kind of internal forces. Okay, so using this force equilibrium, so we can build the relation between the external forces and the internal forces, if any. Okay, and the second condition in the structural scale is displacement compatibility. This displacement compatibility, displacement is 변이, isn't it right? 변이. And the compatibility in 우리말 we call 적합 조건. 적합 조건. Actually, the compatibility condition is very hard. It's not that straightforward to explain what's compatibility, right? What's compatibility? But the compatibility be the relation between the actual displacement vector and then the measure of the deformation, at the material point level. Okay, that's the meaning of compatibility. So another explanation for the compatibility is, for example, let's look at my finger here, or my hand here. Okay, say if I move my finger in this way, so how do you prescribe the deformation of my finger, second finger? Actually, it is hinged here, isn't it, right? The movement of this finger cannot be described with respect to this position, isn't it, right? Because this finger is attached here. So how it doesn't matter how this finger is displaced, the forward or even backward, it is always attached here. Okay, so if I draw the shape of my finger such that my finger is attached here, then it is wrong, isn't it, right? It is not compatible to the concept of my hand. Okay, I wonder if I gave you the concept of comparability, okay? So the concept of a hand should look like this, okay? Should look like this. So whatever the deformation of the or motion of the my hand, is it right? This is comparability. And using, once you have the condition for the force equilibrium and comparability, then you can move our attention to the material point level, okay? So material point level, we have only one condition, the constitutive equations. Constitutive equations or the material law. The constitutive equation is called 구성 방정식. Well, sometimes we call the material laws, okay, material laws. 재료 방정식. Or sometimes we call 재료 model. So usually these constitutive laws are given in nonlinear forms because the material behavior is nonlinear. But in this classroom, so we want to use linear elasticity. By the way, somebody is calling me. Wait a second, please. 여보세요. 수업 중입니다. 예, 수업 중입니다. 네. Sorry about that, because I'm teaching this class sitting in front of my desk. That's why I have I have a phone call. Alright, now let's talk about chapter 1. Chapter 1 is tension and compression and shear. So before we move to chapter 1, so I'd like to take 10 minutes break. By the way, do you have any questions? Then please let me know. By the way, how do you like my iPad? Does it look better? By the way, do I have international students in my classroom? Oh, you like it, huh? What 동현이, what do you mean, the? Do you mean, did you take one of my class in the last year? 주승이, yes, yes, you can buy the SI version. Because, you know, except USA, everybody uses megapascal and Newton, kilonewton. So I'm really happy because my writing looks better. Changho, usually it is based on the absolute scale. So I prefer the absolute scale, but because of the COVID-19, I have to consider some relative evaluation. So otherwise, it is very difficult to put a grade according to your absolute scale of grading. But for A+, okay, so I'd like to be strict, very strict to the grade of A+. So for example, so if you want A+ with like, for example, 60% of your grade, then it is, for me, it is very difficult to give you A+ credit. So A+ is A+. So at least you need to get good credit to ask A+ credit. Alright, so can I go back to the class? Alright, so let's talk about chapter 1. Chapter 1 is for tension and compression and shear. So we'd like to... by the way, Sumini, it's really good question, okay? It's a real good question. So when I talked with the department office, so because the number of students in this classroom is less than 100, okay? So I have less than 100 students in this classroom. So which means, technically speaking, I can do offline lecture. So I really, as I told you, I really prefer to the offline lecture. So I won, okay? But the department office explained me that I can do that. I can do online lecture, provided that so all the students completely agrees to the plan of offline lecture. So what's your opinion? Do you want offline lecture? So I really like to do. So please let me know. It's okay, yeah. So if anybody doesn't like the offline lecture, so we will go to the online lecture in the remaining semester. It's okay. So the default option is online lecture because of COVID-19. How about other students? Alright, so not many response for the choice of the lecture style, whether it's online or offline. Okay, now let's talk about chapter 1. Chapter 1, as I told you, we're going to talk about tension and compression and shear. So basic concepts regarding the analysis. Alright, here we have learning objectives. First, we want to define what's mechanics of materials. So I emphasize the importance of the mechanics of materials before this class. And then we'd like to study the concept of normal stress and normal strain. Here, normal stress is called 수직 응력. Okay, the normal strain, 수직 변형률. This is a counterpart. And then the key properties of various materials. To define materials, types of materials, so we have to define, we need to have so-called material properties. And to define these material properties, we need material parameters. Okay, so material parameters in 우리말 재료 변수, or sometimes we call 재료 상수. Actually, if you translate material parameters, 재료 상수 is better, but we use in Korean, we use the 재료 변수 and 재료 상수 in a mixed way. Okay, the first one is elastic modulus. So if you measure the material behavior, please recall my diagram here. So in the material point level, so we have a relation between the stress and the strain. Okay, stress and strain. At this moment, because I haven't explained you what's stress and strain, but anyway, so please understand that at material point level, so we measure the response of the material in terms of stress and strain. Okay, so I will explain you the concept of stress and strain later. Then if you plot all the response, okay, all the response, initially we have strictly linear elastic behavior, and then this slope is called elastic modulus. Okay, the modulus of elasticity. So modulus of elasticity in 우리말 탄성계수. So once it reaches to the limit of linear elasticity, usually the material shows nonlinear inelastic behavior like this. And depending on material, sometimes we have large strain, or sometimes we have very brittle behavior. And then here the final limit, this stress value is yield stress. The yield stress in 우리말 항복 응력. Okay, the yield means 항복. And then the material, the behavior reaches its ultimate value. This is called sigma u. This is called ultimate stress. 극한 응력. And then depending on articles, depending on reference, and then this 항복 응력 sometimes is written by F sub y, and then the ultimate stress F sub u. Okay, and these are called material parameters. 재료 상수. And then this is for the normal stress and normal strain. These are for normal stress and normal strain. And then as the counterpart to the normal stress, we have shear stress and the shear strain. The shear stress is called 전단 응력. And then shear strain is 전단 변형률. And then here the shear modulus, the shearing modulus of elasticity is called 전단 탄성 계수. Now, similar to this, so if you measure the response between the 전단 응력 shear, 전단 응력 is represented by the Greek letter tau, and then 전단 변형률, the shear strain, is represented by Greek letter gamma. So if you plot the response between the shear stress and shear strain, then we're gonna have a relation. So in general case, we have inelastic behavior, but if you pay attention to the initial behavior between the shear stress and shear strain, then we have certain slope. But this slope is called 전단 탄성 계수, shear modulus G. Is it clear? Okay. And then this is for the shear behavior. Okay, shear behavior. So this is for normal behavior, and this is for the shear behavior. And then we'll talk about Hooke's law for the normal and the shear stress and the strain. And here's Hooke's law is a kind of material law here. Okay, Hooke's law. The Hooke's law deals with only, let me check, different color. So Hooke's law consider only the initial branch, okay, initial linear elastic branch, and that relation is given by the Hooke's law. So make sure that Hooke's law is not this hook, okay. This hook is where did you see this hook? Captain Hook, huh? And Peter Pan. I'm not talking about the Captain Hook in the Peter Pan story. So this is Hooke's law. Okay, according to Hooke's law, the stress is proportional to the strain, isn't it right? So if you want to write instead of this proportionality condition, if you want to replace this proportionality condition to equal sign, then what do you need? We need proportional coefficients. Here the proportional coefficient is given by this elastic modulus, okay, elastic modulus, and this is called Hooke's law, okay, Hooke's law for linear elasticity. And then the response between the stress and strain is linear, and also elastic. That's why this is called linear elasticity. In 우리말 선형, the linear means 선형, isn't it right? The elasticity means 탄성, 선형, 탄성, okay? The similar to this. So if you write the same Hooke's law for the shear stress and shear strain, we have what? The shear stress is equal to the shear modulus times the shear strain, okay? This is the Hooke's law for the shear behavior. Do you have any questions? Any questions? So I feel rather dizzy, for doing my lecture after a long time of vacation. Is it clear? Okay. So this here the concept of mechanics of materials. So mechanics of material is a branch of applied mechanics. Applied mechanics. The applied mechanics means what? So applied mechanics means we want to use some certain kind of mathematics. Okay. So minimum level of mathematics. So nobody likes, for example, nobody likes the partial differentiation integration. Nobody likes that. Okay. So me neither. So we have this differentiation and integration in this classroom too, but the minimum level of mathematics. Okay. So using the minimum level of mathematics, we'd like to deal with the behavior of solid bodies subject to different loading conditions. Okay, that's what we want to do. So if solid bodies are subjected to some kind of externally applied load, then what happened? The body would deform, isn't it right? So in the case of mechanics materials, so we'd like to discuss what would be the displacement as the consequence of the deformation of the body subjected to the various load conditions. And then once we have displacements, then we can calculate the corresponding strains, and then also we can calculate corresponding stress value. Okay, please go back to my diagram. This diagram is really versatile. So once you have information of displacement, then every relation is one-to-one. Once you have displacement, then I can calculate the stress value, strain value corresponding to that displacement field. Okay, so my diagram is one-to-one relation. So do not think many different things at the same time. So you consider only one condition at the same time. At the same time, just consider one condition. So once you have displacement, so you calculate the corresponding strain, and then once you have a strain, then toss the strain to the constitutive model part to calculate stress. Okay, and this is the flow of information. And once you have stress, and the stress is tossed to the part of force equilibrium, and then you check the force equilibrium to satisfy the so-called equilibrium condition. Then you can finish your analysis. Or you can start your analysis from the force equilibrium. From force equilibrium, for given external forces, you calculate the possible set of the stress field. And once you have stress field, the stress field is tossed to the constitutive loss, and you calculate the strain value. And then your strain value is tossed to the displacement comparability to calculate displacement. This is flow of analysis. Okay, so if you want, you can follow this path. Okay, this path, or you can use this path. Okay, so either path is okay for your analysis. Is it clear? So first, use displacement comparability, and then constitutive equations and the force equilibrium. This is the first the way of analysis for structural systems. And the second way of analysis, second flow of information, is starting from the force equilibrium, and then stepping over constitutive equations, and then you finish your analysis by checking the displacement comparability. Any questions? All right. So this is general problem solving approach. The first, we have to conceptualize idealize the problems. Okay, for example, if you have beams, we'd like to represent the structural system in one-dimensional problems, and then you apply the loading conditions to identify the external forces, and what's the support conditions. For example, your structure is, the deformation of your structure is freezing or not, or limited amount of displacement is allowed. Then you have to idealize all the conditions. Okay, and then step 2, then you need to identify what are unknowns in your problems, and then once you have unknowns in your problems, you apply the 3 conditions to solve your mechanical systems. Okay, and then once you finish your analysis, then you have the answer to the questions. What would be the stress value, what would be the strain, and what would be the displacement. That's what we have to do. This is a general approach to solve structural analysis system. Actually, that comes from your textbook, but actually this is a really good approach. And then, but please keep in mind this diagram. Okay, this diagram is a really useful diagram. Any questions? All right, so now let me start to explain the procedure of analysis by using by checking again the 3 conditions. Okay, as I told you, so we want to consider force equilibrium and displacement comparability and the material law. Okay, so we can start our analysis from here to here, or we can do our analysis starting from the force equilibrium, and we finish our analysis by checking the displacement comparability. So we can do either way. Alright, so now I want to explain you the force equilibrium. Okay, so what's force equilibrium? So let's imagine I have a two-dimensional coordinate system here. Then, for example, let's imagine a guy here. Then I'd like direction of the left hand and as an x direction, and then the head direction is y direction. Okay, this is two-dimensional space. And then if you imagine a body whose mass is given by m, and then the body is moving the initial speed v0 in certain angle. So if you write the movement of this body in vector rotation with respect to this coordinate system, so I have mv0 and x component, so x component, and the mv0 the y component, and then each part is multiplied by the unit normals in x direction and y direction. Okay, so before what I mean, we have this vector. So before we define this coordinate system, so what we want to do is we'd like to explain the momentum of the body with respect to this chosen coordinate system, isn't it? That's why we have to consider the projection of this vector into this coordinate system. So Ex means unit normal in x direction, the Ey is unit normal in the y direction. This is the x component, so V0 times cosine theta naught, and then V0 times sine theta naught. This is the y component of this vector. Is it clear, right? This is momentum. And the definition of the force, for example, let's imagine the particle, the body is in contact with this wall, and then because of this contact interaction between the body and wall, so eventually the direction of the movement is changing to the other direction. For example, initially I have the theta naught, and then after contact, so we have new direction theta 1, which means we have change in the momentum, isn't it? The change in the momentum. The force is defined by change in the momentum. So before the contact, we have P0. Okay, P0. This is P0. Then after contact, we have new momentum. So let's measure the change of momentum. So you can measure the change of momentum V1 cosine theta, the V0 cosine theta naught, blah blah blah. Okay. We just subtract the initial momentum from the momentum after contact. So if you take a derivative, the change of momentum with respect to time, then we can obtain the definition of force. So make sure that here momentum is a vector, isn't it? The mass times the velocity vector, and that's why the time derivative of vector becomes a vector. That's why the force is a vector. So make sure that the force is a vector. Okay. So the momentum is a vector. Momentum in 우리말 운동량. This is a vector. Okay, vector. And then the forces. Force. 힘. Because the force is defined as the time derivative of 운동량. So which means this is also a vector. Is it clear? So in a special case that the mass is not changing, mass is given, only the velocity changes. So from this diagram, the mass is constant, but the velocity changes. So if you take this derivative, the time derivative to the velocity means the acceleration, isn't it, right? Acceleration. That's why the force vector is defined by force vector. So underbar means vector, okay? Underbar, one underbar means we use one set of the unit vectors, E, X, and EY. Okay, that's the meaning of underbar. is equal to mass times acceleration vector. Okay, so time derivative of the velocity vector is equal to acceleration. The acceleration here, this guy is called 가속도. Okay, let me talk about this notation. F bar means, as I told you, I have one set of unit vectors, which means so fx components times ex, the normal vector in x direction, plus fy component ey direction, the fz component ez direction. Look at the 3 dimensions. Okay, I have one set of unit normals. Okay, because I have one set, I want to put one bar. Is it clear? And instead of x, y, z coordinate system, instead of that, we, for example, okay, let's consider 3-dimensional coordinate system. So x, y, and z, and that's what I use to define this, isn't it? But instead of x, y, and z, maybe we want to use x1 and the x2, x3. Okay, so many people, me too. So I prefer to use x1, x2, x3 instead of x, y, z. Okay, so in that case, we have the same force vector is written by f1, e1, f2, e2, f3, e3. So this is called indicial notation. Okay, indicial notation. Indicial notation means index notation. Okay, indicial notation. Because we represent the different axes by number, it can be further simplified by using summation sign. So I from 1 to 3 and fi, ei. So instead of use capital I, if you want, we want I 1 to 3, so fi and ei. Okay. Of course, if you don't like I, so I cannot use I want to use J. It doesn't matter. J, no problem. Or KK, whatever. Okay. Alright, so let's consider this case. This case, because of V naught is changed to V1, okay? During this contact, the velocity changes, which means the acceleration is not constant. So acceleration, we have non-zero acceleration. So in this dynamic event, so here, before the contact, so after the contact, there's no change in the acceleration. So if acceleration is equal to 0, then sum of force is equal to 0. If no change in the velocity, the sum of all the forces, acting into body is equal to 0. No change in the velocity. Okay, this is called 평형방정식, force equilibrium. What does it mean? Does it mean statics? Actually, it doesn't mean real statics. Okay, it means no change in the velocity, which means if you have any system moving with constant velocity. Okay, let's look at my pen. Okay, if you have a pen, let's say my pen is moving with a constant velocity. Okay, constant velocity. Then in that case, the sum of forces applied to the acting on this pencil should be equal to 0 because there is no change in the velocity. So of course, if I apply the boundary condition to the end of my pencil so that the pencil is not moving, okay, then in that case, we apply the force equilibrium for the static system. So please make sure that the sum of force is equal to 0. The force equilibrium is not applied to real static condition, real steady state condition, but but also the system moving with constant velocity. Okay, this is the force equilibrium condition. Now let's discuss further. The first example that I'd like to discuss with the use of Newton's apple. So if you look at Newton's apple, let's look at the free body. Let's look at this apple. It's falling down this tree. So if you look at this apple is subject to gravity loading. So mass times the gravity acceleration. Then what? This is the consequence, isn't it, right? So this is the force applied to this apple. So which means I have mass times, the force equilibrium condition look like this. The acceleration of apple should be equal to applied force. This is mass times the gravity. So here the mass is cancels. So acceleration of this apple is given by the gravity. Okay? Isn't it? This is the force equilibrium. But let's consider another case. This apple is attached here, not falling down. But because of gravity, I have some, the gravity loading, mass times the gravity acceleration. But this guy is not moving. So not moving means acceleration is equal to 0, isn't it? The sum of, let's say, consider this system. So for example, I need to consider the force 1 and the force 2, force 3, force 4, whatever. So we can consider numerous kinds of forces. Okay, so let's consider first force 1. Maybe this force, maybe this guy can be the gravity, isn't it right? From this falling apple, so we identified the external load. This gravity is kind of, external load. In 우리말 외부 하중. Okay? Gravity, by the way, gravity is 중력. Alright, so this is my apple. Okay, and then my apple is attached to this tree. Maybe I may have some reaction, isn't it right? Reaction to the tree. The reaction is called 발력. The reaction to the tree. And then how about in the reaction in the vertical direction? Let's say in the vertical direction. And also we can imagine any reaction in the horizontal direction. Well, any possible reaction. So unknown action, okay, unknown forces caused by the external forces to satisfy the force equilibrium. Reaction in the horizontal direction. The horizontal means 수평 방향. The vertical means 수직 방향. Okay. Well, if you want, you can consider many different things, like for example F3, for example, the wind load, for example, yeah, the wind applied to the apple, and also F4, for example, you can consider the any snow load applied to apple. Okay. So when you harvest any apple, there's no snow. Well, anyway, you can consider wind and snow, whatever. Okay. So now let's focus only up to here. The gravity and the reaction in the vertical, the reaction in the horizontal direction. Alright, so according to the force equilibrium, for the static system is not moving. The acceleration should be equal to 0. Look at this. This is force equilibrium. Sum of force should be equal to 0, isn't it? Here the acceleration is equal to 0. So F1 plus F2 plus F3 is equal to 0. Now let's write F1. Alright, so F1 is a vector, isn't it, right? So I said the gravity. This is a vector. I have an arrow, okay? I have an arrow here. So, but to write this vector calculation, I need to define a coordinate system, isn't it? So let's consider this coordinate system. This is, say, x direction. This is y direction. So F1 is given by the magnitude is mass times the gravity, isn't it, right? Mass times the gravity acceleration. And then what's the direction of unit normal? Defined by this coordinate system is upward, isn't it, right? EY. Okay? So we need to multiply the unit normal, EY. Isn't it? EY. And then what's the meaning of mg times EY? The direction of this vector is heading upward, isn't it? But my gravity load is heading downward. Okay, that's why we need to put minus sign. Okay, so exactly speaking, the minus sign, so minus sign should be attached to here. So minus sign is here. Okay, so if you put the minus sign, it moves its position. Then it becomes minus mg times EY. Is it okay? And how about F2? F2 is reaction. So reaction means we don't know whether whether it is upward or downward. I don't know that. Okay, so that's why this is unknown value. That's why I want to say its magnitude is Ry. Okay, I don't know its direction, but so we'd like to choose a default direction. What's the default direction? Default direction is given by my coordinate normal, so EY. Okay, I don't know that. Okay, I don't know that. I have to check the force equilibrium. And now how about third one, F3? Again, this is a reaction in the horizontal directions. Again, I don't know the magnitude Rx. Okay, so we just choose the default direction, Ex. Okay, then let's write all these equations in vector notation. I have minus mg EY, and then I have F2, so Ry the EY, and the plus Rx Ex is equal to 0. Okay, let's collect for each unit normal. So I have Rx Ex and the plus Ry minus mg EY is equal to 0, isn't it? So make sure that there's no way to represent, EY using Ex. So make sure that they are orthogonal. Okay. So orthogonality means we cannot represent EY using Ex. Also, we cannot represent EX using EY. We cannot do that, okay? That's the means of orthogonality. That's why to satisfy this identity condition, all the coefficient associated with EX should be equal to 0, and all the coefficient associated with EY should be equal to 0 at the same time, okay? So which means because of this orthogonality condition of the choice of coordinate system, so Rx, this guy should be equal to 0, but the unit normal cannot be equal to 0 because this is a constant, isn't it? Constant vector. That's why only condition which satisfies this identity condition is Rx is equal to 0. Is it clear? Okay. And how about this? So again, by the same logic, this guy is already given. This is a constant vector. That's why to satisfy this identity condition, this guy should be equal to 0. So Ry is equal to mg. And this is analysis of reaction. Calculation of reactions. 반력. So according to this calculation, the reaction in the horizontal direction is equal to 0. The reaction in the vertical direction, its magnitude is equal to gravity loading, mass times the gravity. Okay? Any questions? Is it clear? Any questions? Oh, good. All right, so I'm very happy. It seems that you are following very well. So let's extend, let's generalize the Newton's apple into a one-dimensional system. So I have a hanging mass, and to a post. So you can imagine this is a tree. Look at this tree, and then the apple is idealized to hanging mass, okay? And this mass is subjected to the gravity loading as before. So I want to consider the system, so ABC here, ABC. So if you apply the force equilibrium, you can easily calculate the reaction. So its magnitude is equal to mass times the gravity loading, isn't it? So we did this operation, okay? So we calculated the force equilibrium for the choice of system. Okay? And then I wanna focus only the B. Okay, this is the first choice. I wanna focus only the B, C. If you focus B and C, again the reaction we calculate at point B is also calculated as its magnitude is equal to mass times the gravity. Is it clear, right? So if you do that, okay, so for big system, it is subject to mass times the gravity. And then here, this guy is equal to mass times gravity, isn't it? To satisfy force equilibrium. So this is point A and C and B. So if you consider smaller system, and then it is subject to the mass times the gravity. And then if you consider force equilibrium again, so we can conclude that this is equal to mass times gravity. Okay, mass times gravity. All right, now problem is, let's look at AB segment. So if you look at AB segment, point A and point B. Alright, so what's Newton's third law? Newton's third law says that action and reaction, isn't it? So we must have exactly same amount of force in the opposite direction, this direction. Mass times gravity, okay? And then here we need to have mass times gravity. Okay, so depending on choice of my structural system, so we can identify all the force components acting on the choice of the body. Okay, so we call it free body diagram. Okay, in 우리말 자유물체도. This is the concept of free body diagram. And then this free body diagram concept can be applied to other complicated system too. So let's imagine a girder. The subject to vehicle load. So if you weigh the vehicle, then maybe its weight is measured as F. And make sure that I use boldface to represent this as a vector. Okay? Because of gravity loading. If you put a coordinate system here, X and Y, then I can put the weight times the direction of loading. Because I have non-zero force, okay, non-zero force, if you choose a large free body diagram to satisfy the force equilibrium, because I have non-zero force, then I need to have unknown force, isn't it, at the support. And I must have also unknown force, okay? Whether the force can be zero or it can be non-zero values, anyway, to satisfy the force equilibrium, the sum of force should be equal to zero, okay, to satisfy this. Then I need to have some certain kind of reactions. So using this relation, so we have to calculate the magnitude, the specific value of the reactions. Of course, for this problem, so we have RA, unknown reaction, plus so RB, also unknown reaction, isn't it? And then external force is equal to zero. So I have one equation and two unknowns. So which means with this condition, we cannot solve this system. So anyway, I'd like to show you the general relation between the external force and the unknown reactions. And then if you choose the smaller size of force, the free body, so like omega 1. So let's imagine the boundary of omega 1. Let's say I want to call it gamma 1. And then at the boundary, because this part is attached to omega 2 here, and there must be also some forces, okay? So also some forces. And of course, these forces are, the internal. So that's why these forces are called internal forces. Of course, these are unknown too. Internal forces. In 우리말, 매력. So counterpart of internal forces, external forces. 외력, okay? 매력 and 외력. Somebody's calling me. Wait a second. 여보세요? 예, 수업 중인데 잠깐만요. 좀 빨리 hold on. I'm sorry about it. This is, as a side effect, this side effect for online lecture, because I'm giving my lecture in front of my my computer, so many people are calling me in the office phone. I'm sorry about it. So you understand the concept of internal forces and external forces. Okay, external forces are given. Okay, apparent. Okay, apparent forces. But internal forces, a certain force. Okay, a certain unknown force component required for satisfying the force equilibrium. Okay, defined on the boundary of free body diagram. Okay, this is different choice of free body diagram. Any questions? Okay, so now let's discuss the structure of equilibrium equation. Okay, so again, I told you that. Again, I told you that force equilibrium is a vector form of equation. So here, so we have to consider sum of all the force vectors should be equal to 0, as I did here. Okay, so we have to check all the forces, and also we need to check the moment vectors too. We have forces, and then also we need to check the moment vectors too. So moment vectors is defined by the cross product of force vectors and then the position vectors, and this guy should be equal to 0. What's the counterpart of force? The force is associated with displacement, isn't it, right? And the moment vector is associated with rotation. The rotation is also a vector part. And then in scalar form, so once we have this vector equation, we can check the force equilibrium in the component form. So all the components in x direction should be equal to 0. All the components in the y direction should be equal to 0. And all the components in z direction should be equal to 0. And then, as I told you, instead of x and y and z, you can use indicial rotation. And also we can write, instead of each equation, we can use the summation notation too. And for the moment part, also we can do the similar way. All the moment part for the x and y and z, each of these should be equal to 0 to satisfy force equilibrium. And instead of using x and y and z, we can use the indicial coordinate system. Should be the only notation problem. As I told you, this three-dimensional coordinate system can be defined two different ways: x and y and z, or you can consider x1 and x2, x3. Okay, this is more general, isn't it? So x and y and z, this is a traditional style as given in Timoshenko's textbook. That's why if you open your textbook, it uses x and y and z. In the advanced articles published recently, they use x and y, x1 and x2 and x3. This is more general. And for applied forces, applied forces in 우리말 작용 하중. 또는 작용 힘. Okay, the same meaning. Okay, 작용 하중, same meaning. The first one is concentrated forces. Concentrated forces, a concentrated moment is called. What happened to the color? Oh, sorry. 집중 하중. For instance, so we have a force at a very, very small point, like for magnitude of force is like 10 kilonewton. Okay, this is called 집중하중, concentrated forces. And if the force is given in terms of moment, we call it concentrated moment. And then the other concept is distributed forces. 분포하중. Okay, for example, the force, same magnitude of force is applied over an area. So for example here, let's say same 10 kilonewton. Let's imagine this area is given by A naught. F times A naught. Okay, F times A naught. Then F is defined by 10 kilonewton divided by A naught. So in that case, here this F, small f, is called 분포하죠. And this distributed load can be defined over a line. This is another distributed load, okay? Sometimes distributed load over the volume, so volumetric loading. And then I already explained you the concept of free body diagram. And the fourth concept is static sign convention. So do you remember? Say we have force vector. Let's imagine I have vector r, okay? So I have numerous ways to represent this vector. For example, let's define a blue coordinate system. So if you define blue coordinate system, x1 and x2, then this is E1 and this is E2. So how do you write this r? Then vector r can be written by the let's consider projection. Projection to this direction is, this is what? This is, the projection is r1, isn't it, right? In r1 times E1. And also let's consider projection. By the way, projection is called 정사형, okay? 정사형. And plus r2 and E2. Isn't it? Or let's consider another choice of coordinate system. For example, I want to choose this coordinate system, x1 and x2. So we have numerous ways to define the same vector, okay? Once you choose a certain coordinate system, so the vector component must be defined with respect to the choice of the coordinate system. Then red R1, the red R1 is here. This is the red R1. And times, so this is E1, red E1. Plus red R2, this is projection to here, R2, and then E2. So make sure that here, the red R1 and then blue E1, red R1, they are red E1, sorry, they are different, okay? They are not the same. You understand? For the same vector, the vector component representation depend on the choice of our coordinate system. Is it clear? You understand? This is really important concept. So which means the sign of a vector should be determined by the choice of coordinate system. Look, so let's imagine I have a vector. Let's say in that direction I have 10 kilonewton. So if you choose this coordinate system, for example, let's say I want to choose x1, x2, or if you want x and y, then in that case this is parallel with the unit normal one direction, or ex direction, parallel. Its magnitude is equal to 10 kilonewton, so which means this vector is written by 10 kilonewton and times E1, isn't it, right? So its direction is the same as the direction of unit normal. That's why its sign is positive. Is it clear? But that's because the same vector. So if you choose this coordinate system, say this direction is x1 or x, and then this is x2 direction and y. So with this choice, the direction of unit normal is here. It's E1 or EX. So in that case, its magnitude is same, 10 kilonewton, but its direction is in the right hand direction. How do you represent the right hand direction? Using this. Then minus direction of E1, isn't it? That's how we represent this. This is equal to, if I move the minus sign in front of this equation, minus 10 kilonewton E1. Okay, so in that case, I have minus value by the choice of another coordinate system. Make sure that for the same vector, the sign of the vector depends on the choice of coordinate system. Is it clear? This is really so much important concept. How about other students? And then this is a way of representing the reaction forces. The reaction forces, they are unknown, kind of unknown, okay? Because we don't know the unknown. Usually we consider the default choice of reaction forces, okay? So parallel to the direction of coordinate system. Okay, this is really easy. All right, so here I wanna stop my lecture here. Let me finish up to the internal forces. So here we already discussed the concept of internal forces, okay? When you draw a line across a structural body, then because to satisfy the force equilibrium, we must have some force component inside the structural body. This is called internal forces. Again, this is internal forces comes from what happened inside. So we have to describe the internal forces with the concept of stress. That's why I don't want to explain it today. Okay, so let me stop my lecture here. Do you have any questions up to today's subject? By the way, we have TA class on Monday. Theory class on Wednesday, okay? And then TA class on Monday. Any questions? By the way, look, for example, if you move my lecture note all the way back here, then we have homework problems. Okay, homework problems, and then the TA problems. My TA will solve for these problems, and you need to solve these homework problems. So homework problems are already given here. Okay. So depending on the speed of my lecture, the progress of my lecture, so you have to solve these problems automatically. Other questions? Of course, yes. How about other questions? So if you don't have further questions, let me stop my lecture here today. The next time we'll discuss the concept of the normal stress and normal strain, and then we'll also discuss the normal strain, and then we'll solve some examples, and I will explain you so how we measure the stress and strain from experiment to identify the material behavior. And then I will explain you what kind of material properties that we handle to describe material behaviors. And I will explain you the typical, the stress strain diagrams of different materials. This is for steel. 수민이, 블랙보드에도 과제 공주와 듀 업데이트가 나가나요? 블랙보드 과제 올리나요? 아니요. Wow, you are so detailed. So I'd like to ask you solve the problems in your note, and please send my TA the scanned copy of your homework problems. Is it okay? So I think either better you can talk with my TA next Monday, because my TA would have his own style. Okay, then let me start my lecture here.